This recording is going to be the review questions from Chemistry Chapter 5. And as before, we won't be doing all of the review questions, but just those that involve some type of problem. So we'll start with number 3. And number 3 lists 7 molecules, and we are asked to draw the Lewis structure for those. So 3A is F2, so that's fluorine. And if you look at the periodic chart, you will see that fluorine is in group 7A, so it has 7 valence electrons. So in terms of the Lewis structure, this would be a covalent bond, and these two atoms would just share that electron. So then we could draw it like this. Okay, so by sharing that one pair of electrons, each of the fluorines will have 8 valence electrons at least part of the time. Okay, then 3B is this. So if we draw the Lewis structure for oxygen, oxygen has 6 valence electrons. And then we have 2 chlorines, and each chlorine it's in group 7. So each chlorine has 7 valence electrons. So putting these together, this and this can be shared. So we'd have the oxygen there sharing that pair of electrons, and then this can share with that. So that would be like that, and then each of them would still have the groups of paired electrons that they had on them. Okay, so this would be the Lewis structure then for this molecule. Okay, the next one is a nitrogen. The molecule is made of a nitrogen, a hydrogen, and 2 iodines. Okay, so we'll put the nitrogen there. Nitrogen is in column 5A, or it's in group 5A, so it has 5 valence electrons. Hydrogen has just 1 valence electron. Then we have 2 iodines, and iodine is in group 7A, so each iodine will have 7 valence electrons. So the nitrogen will be our central atom because it has the greatest number of unpaired electrons. So we compare this unpaired electron on the hydrogen with an unpaired one on the nitrogen. So there's that. So we got rid of that. And then each of the iodines has 1 unpaired electron. So we compare this one, and this one. So we can move that iodine over there. Let me go ahead and erase this. And move that iodine over there. They can share that pair of electrons, and then iodine will still have the other 6 valence electrons, and then this unpaired one on that iodine can share with the remaining unpaired electron on the nitrogen, so that becomes that bond there. And then again, iodine will have the rest of its valence electrons. Okay, so that is what that molecule would look like. Let's clean it up here a little bit. Okay. And so if we look at this, we can see that hydrogen has its 2 valence electrons. Nitrogen has 2, 4, 6, 8. Each of the iodines also has 8 valence electrons. Okay, the next one is S2. So S is sulfur, and it has 6 valence electrons. So we have 2 sulfurs, each with 6 valence electrons. So we compare the unpaired electrons. We can join the unpaired electrons, so we can join these 2 and make a bond, and then we can move this one and this one into the middle and make another bond there. So this is the sulfur molecule, the sulfur atoms are bound together with a double bond. So this is a double bond. And each of the sulfurs has its 8 valence electrons. 2, 4, 6, 8 for that one. 2, 4, 6, 8 for that one. Okay, the next one is a carbon, a sulfur, and 2 iodines, ICSI2. Okay, so carbon has 4 valence electrons. So that means it also has 4 unpaired electrons. S is sulfur, and it has 6 valence electrons. And then we have 2 iodines, and each of those is going to have 7 valence electrons, because on the periodic chart they're in group 7. Okay, so there's the Lewis structures for each of them. So again, carbon's going to be our central atom because it has the most unpaired electrons. So let's start with these iodines. Since they each have 1 unpaired electron, let's bring those over here and share this electron, 1 electron with the carbon, and then we'll do the same thing with this one. We'll take this unpaired electron, bring it over here, and we'll share that with that carbon. So we'll draw that as a bond like this. Okay, so we're done. We've used up the iodines, and then let's go ahead and put the rest of the valence electrons on the iodines. So we had 6 that were paired. Okay, then we have this sulfur that has 2 unpaired electrons, and we have the carbon that has 2 unpaired electrons. So we can move all of those electrons into the middle. And then these can share those and create a double bond there. And so carbon now has 2, 4, 6, 8 electrons. The iodines have 8 and this sulfur has 2, 4, 6, 8 valence electrons. Okay, the next one is N2. So we're going to have 2 nitrogens. And first of all, you should recognize that nitrogen is one of our homonuclear diatomics. So remember we said that when it's just nitrogen that is making up the molecule, you always have 2 of them. It will never be just a single nitrogen. Okay, so nitrogen is in group 5A, so it has 5 valence electrons. And the other nitrogen the same, 5 valence electrons. Okay, so each one has 3 unpaired electrons, so we can just move those all into the middle. Erase the whole thing there. So they each have 3 unpaired electrons, so let's just move those into the middle and make a triple bond with those. So we would have a triple bond with the nitrogens there, and then each of them would still have these other 2 valence electrons, so that they both have 8 valence electrons at least some of the time. Okay, then the last one for number 3 is H, a silicon, and a phosphorus. Okay, so hydrogen is in group 1A, so it has 1 valence electron. Silicon is in group 4A, so it has 4 valence electrons. And P is phosphorus, and it has 5 valence electrons. I didn't draw that right, let's see. Okay, so it has 3 unpaired. So this one's fairly easy because we can compare this, we can pair up the hydrogen and the sulfur at their unpaired electrons, and then that leaves the silicon and the phosphorus each with 3 unpaired electrons, so we can move all of those into the middle and create a triple bond. Okay, so they each have 3, so we move those into the middle and create and you'll have a triple bond there. So again, if we look at the phosphorus, it has 8 valence electrons. Silicon has 6 on this side and 2 on the left side. That gives it 8, and hydrogen has its 2. Okay, the number 4 asks us to name a series of compounds. So the first one is this. Okay, so the first thing we notice is those are both nonmetals, so it's a covalent compound. So we would name it by giving the first word sulfur, and then the second one we're going to add a prefix, and the prefix for 2 is di. So this would be sulfur dioxide. And the next one is this. So we'll start with this. So they're both nonmetals. So this would be phosphorus. And then the prefix is going to be tri. And it's hydrogen, so it would be trihydride. Phosphorus trihydride. Okay, the next one is potassium. Okay, so the first, what you need to notice about this is an ionic compound. So because it's a metal and a non-metal, so we will use the rules that we learned for ionic compounds, and that is the first one just gets its name, so it's potassium. And then the next one we just add the ending "ide." Okay, so no prefixes with an ionic compound. Okay, next is P2O5. Okay, so this first one, we do use a prefix unless it's one. So this would be diphosphorus. And then for that 5, it's going to be penta, and then oxide. So diphosphorus, pentaoxide. Sometimes you'll see this just leaving that. It would just be pentoxide. Either one of those would be okay. Okay, so diphosphorus pentoxide or pentaoxide. And then the next one, the last one for number 4 is this. So it's covalent because they're both non-metals. So this would be dinitrogen. Trioxide. So again, on that first one, if there's more than one, you do use a prefix. If this were just a single nitrogen, we would just say nitrogen. But because there are 2, we do use a prefix. We always use a prefix for the second one with the ending "ide." Okay, let's skip down to number 11 now. And we're actually going to combine here numbers 11, 12, and 13. So number 11 asks us to determine the shape and draw a stick figure, and there's 6 different molecules. And then number 12 asks us to indicate whether it's a polar covalent or purely covalent molecule. And number 13 then asks us for each one whether or not it would dissolve in water. Okay, so we'll start with A. We'll just answer all 4 of those questions together. Okay, so silicon is in group 4A, so it has 4 valence electrons. And then we have 4 chlorines. And chlorine is in group 7A, so it has 7 valence electrons. Okay, so silicon has 4 unpaired electrons, and each chlorine has an unpaired electron. So we will just pair up those unpaired electrons and make our Lewis structured molecule look like this. Okay, so I'll go ahead and erase the rest of this. And then, if we were just drawing the stick figure, you'd go ahead and put the rest of the valence electrons on these. I'll just do them for one, but you need to do that for all the chlorines if you were just drawing the Lewis structures. But then for this question, we're asked to determine the shape. Okay, so we look at this and we see that the central atom, which is silicon, has 4 pairs of electrons around it, and none of those are unpaired. So that tells us that it is a tetra, or none of them are unshared. So its shape would be tetrahedral. And that, so if we were to draw that, it would be, we'd put the silicon there, we'd have a chlorine out here, chlorine up here, and then draw the 2 that are pointing out and the one that is pointing back, like that. Okay, so that's the stick figure for a tetrahedral molecule. And then it asks us whether it is polar covalent or purely covalent. So we know that this has polar bonds because the chlorine is going to pull on that silicon harder than the silicon pulls, because chlorine is farther to the right than the silicon on the periodic chart. So it has polar bonds. However, this would be a purely covalent molecule because we're getting equal pull in all 4 directions. So the molecule will be purely covalent, even though there are polar bonds between atoms within the molecule. And then the last question with regard to this molecule is whether or not it will dissolve in water. So the other way that we name a purely covalent molecule is we call them nonpolar. And nonpolar molecules will not dissolve in water. Water is polar, so it's a polar molecule. So because it is a nonpolar or purely covalent molecule, will not dissolve in water. Okay, then 11b is this. Okay, so we have the sulfur, which is in group 6A, so it has 6 valence electrons. And then we have 2 hydrogens, and each hydrogen has 2 valence electrons. So we will share those unpaired electrons between the sulfur and the hydrogen. And our molecule would look like that. So the sulfur has its 8 valence electrons, and the hydrogen has 2. So then this one, we notice that there are, around that sulfur, there are 4 pairs of electrons, but 2 of them are not bound to anything. 2 of them are not paired with anything, and so the shape of this molecule then would be bent. And so the way that we would draw this molecule, we would put the sulfur, and then each of the hydrogens is going to be coming off of that like that. And in this case, the sulfur, because it's farther to the right It's one row below the row that hydrogen is, but it's a lot farther. It's actually 1, 2, 3, 4, 5 to the right. So the sulfur will pull on those electrons harder than the hydrogen. So these are polar bonds, but is the molecule polar? And yes, the molecule is polar because there's nothing, we're pulling from on this direction, but there's nothing pulling, there's no equal pull on the sulfur from the other end. So this is a polar covalent bond, polar covalent molecule. And polar substances dissolve in water. Water is also a polar molecule, and polar dissolves in polar. So yes, it will dissolve in water. Okay, the next one then is, back to where I am. The next one is so GE stands for germanium, and SE is selenium. Germanium, selenium. So these are both non-metals, and so in naming this would actually be germanium diselenide. Okay, that's how you would name it. So let's go ahead and draw the valence electrons for germanium. It is in group 4, so it has 4 valence electrons. And we have 2 seleniums, and selenium is in group 6. So it has 6 valence electrons. And then we have another one. Same thing, 6 valence electrons. Okay, so what we can do with this one is we can take these 2 unpaired and these 2 unpaired and put them on one side of the germanium. So we'll draw it, it'll be a double bond because they each have 2 that are unpaired. So we'll put one selenium over here, and then we'll do the same thing here. We'll take these 2, take this one and this one, move those both into the middle, and then move these 2 into the middle over here, and move this, and that selenium will go over there. Oh, eraser's not working. Okay, so that molecule will look like this, and so 2, 4, and then we go ahead and draw the rest of the paired electrons with the selenium. But the germanium has its 2, 4, 6, 8 valence electrons. Okay, so this shape is linear. And again, the selenium will have a greater pull than the germanium. So we would draw our arrows like this. But in terms of the stick figure, this is linear. And and we would just keep it the way it is. So it's linear, and this would be a non-polar molecule. Because the seleniums will pull on, it's going to be pulling equally from each side. So that's a nonpolar molecule. Nonpolar does not dissolve in water. So this one will not dissolve. Remember, nonpolar is the same as saying a purely covalent bond. Those mean the same thing. Okay, the next one is PF2. Okay, so phosphorus is in group 5A. I'm sorry, it's F3, not F2. So 5. And then we have 3 fluorines. And they each have 7 valence electrons. So each fluorine is going to have 1 unpaired electrons, and there are 3 places on the phosphorus that has unpaired electrons. So we'll just pair up each of those fluorines with one of the unpaired electrons on the phosphorus. I'll make the bond here, put another F over there, and then do the same thing up here. Okay, so that is what our Lewis structure would look like. And of course, you'd have to draw the rest of the valence electrons on the fluorines if you're drawing Lewis structures. Okay, so then to draw a stick figure for this, we see that the phosphorus has 4 pairs of electrons around it, but one of those is not one of those is not bound to anything. So because it has 4 and 1 is not bound, then this would be a pyramid shape. And so we would draw it like this, one coming out like that, and then we'd have the triangular one to indicate that it's going back or going forward, and this one to indicate that it's going back. Okay, so that's the pyramid shape. So then we ask the question, is it a polar or non-polar molecule? So the fluorine is going to be pulling on these harder than the phosphorus because it's farther to the right. Because there's nothing pulling upward on this, you're not going to have equal pole. So this would be a polar molecule. And polar molecules do dissolve in water. So PF3 would dissolve in water. In terms of naming this compound, it would be phosphorus trifluoride. So again, just remember that if the first one, if there's only one of the first one, we don't use the prefix. If there's only one of the second one, you would say mono, but for the first one, you just say phosphorus trifluoride. Okay, next one is H2SiO. Okay, so we have 2 hydrogens and they each have 1 electron. Silicon is in group 4A, so it has 4 valence electrons. And then oxygen has 6. Okay, so let's start by pairing up these unpaireds on the hydrogens with 2 of the unpaireds on the sulfur. So we'll make a bond with one of the hydrogens and make another bond with the hydrogen there. So now that leaves us with 2 unpaired electrons on silicon and 2 on the oxygen. So if we move those into the center on each one of the molecules, so we can move this one, and then we can pair those. So that's what the Lewis structure would look like. So then we look at the central atom, which is the silicon, and we see that it has 3 groups of electrons, and if it has 3 groups, then its shape would be trigonal. And we would draw the stick figure to look like this. So we put the silicon here, we put each of the hydrogens like this, and then the double bond oxygen. And in terms of the silicon's gonna pull harder than the hydrogens, and the oxygen is going to pull harder than, because it's silicon, let's see. Yeah, silicon, oxygen is higher and farther to the right, so it's also going to be pulling more on there. And again, because we're getting pull only in 3 directions, nothing's pulling up or down on this, then this will be a polar molecule. And polar molecules do dissolve in water. Okay, so that finishes up the questions the problems for chapter 5 review.